So the standard change in free energy is the criteria for spontaneity at standard conditions. So there are different ways that you can calculate that. You can calculate standard heat of reaction, standard entropy change for the reaction from the heats of formation and the molar entropy. And then you can plug those into this equation and calculate delta G. You can also calculate it from standard free energy of formation, which you can look up, or we can calculate it from free energy changes for steps if there's a stepwise reaction. So of course we'll look at all of these. Okay? So we can calculate the standard entropy change for the reaction and the standard enthalpy change for the reaction from the tabulated values. And both of those calculations take the same form. We just did an example of this. So you'll look up the standard entropies and standard enthalpies in a table, and you multiply by the coefficients, and you do a little math, and then you plug them into this equation. To be fair, this is actually only valid at 25 degrees Celsius, because that's where those standard enthalpies and standard entropies have been measured, but it's still going to give us an estimate at other temperatures. So let's do an example of this. Consider the oxidation of nitrogen monoxide to nitrogen dioxide. Calculate the standard change in free energy for this reaction at 25 degrees Celsius. Determine whether the reaction is spontaneous at this temperature. So to do this calculation, we have to have some more information available. Now, this sort of information can be looked up on the internet, but I would encourage you to just use the appendix at the back of your textbook. And if you don't like carrying your textbook around and you don't have a digital copy, take pictures of it, right? And then you've got it on your phone or your tablet or whatever, and you can look it at whenever you need it. So calculating delta G, let's remind ourselves, well, we've got the equation right up here. We need to calculate delta H and delta S for this reaction. So let's start with delta H. So delta H for this reaction is going to be equal to the heat of formation for NO2. So I'm going to look that up in this table. NO2, heat of formation, 33.2 kilojoules per mole. So we're taking the heats of formation for the products and subtracting the heats of formation for the reactants. So that's my one product. The moles cancel out. And then I'm subtracting the heats of formation for my reactants. So I have 1 mole of NO, and I have to look up the heat of formation for that, is 91.3 kilojoules per mole. And then I've got 1/2 of a mole of O2. What's the heat of formation for that? 0. If you forget that, when you look it up in the table, it says that it's 0. So 0 kilojoules per mole. So 33.2 minus 91.3. So delta H here is minus 58.1 kilojoules. Okay with that? What does that tell us? It's an exothermic reaction. This is going to release energy into the surroundings that doesn't tell us whether it's going to happen spontaneously or not. Yes?
Are we always supposed to start with NO2?
So delta is always final minus initial. Yeah, so it's products minus reactants. Yep, good question. So then delta S, standard change in entropy. Same process, and those numbers in your textbook are in the same table, right? So we're looking at 1 mole of NO2, and the entropy, standard entropy for that is 240.1 joules per mole Kelvin. So the moles cancel. That's my product, subtracting the reactants. 1 mole of NO. Entropy for that is 210.8 joules per mole Kelvin. Plus 1/2 mole times the standard entropy for oxygen gas, which is not 0, 205.2 joules per mole Kelvin. Moles cancel. What I like about this is the process of doing the calculation. It's the same for both of them. Yay! So I got 240.1 minus 210.8 minus 0.5 times 205.2. I'm getting minus 73.3. And that's joules per Kelvin. Yes?
So on the test, will these, the numbers be given to us in the question or on the formula sheet that you usually have?
Yes. One or the other.
Okay.
Usually I give them to you in the question, because if I give it to you as a table, I either have to do a lot of cutting and pasting or typing, or I waste a lot of paper by giving you the whole thing. So I tend to give it to you in the question, but I could give it to you in a separate table. Yes?
You said that if both of them were negative, that we could find if it was spontaneous or not by the temperature.
Mm-hmm.
How do we find that right now?
Well, we have to plug these two things into this. Yeah, we just have to solve for delta G and find out. Yeah. And because they're both the same sign, this is going to be spontaneous at some temperatures and not at others. Okay, so now we can calculate standard change in the free energy. It's delta H, negative 58.1 kilojoules per mole. No, just kilojoules, sorry. Minus the temperature, 25 degrees Celsius, it's 298 K. That one comes up so much that I just remember what it is. Times delta S. So here we've got delta S. Again, this is joules, and the other one is kilojoules. And I think kilojoules is a better choice because I'm subtracting this thing from kilojoules, and so kilojoules is probably going to be a more appropriate unit. So this is going to be negative 0.0733 kilojoules per Kelvin. So I've got negative 58.1 minus 298 times negative 0.0733. Getting getting negative 36.3 kilojoules. Is this reaction spontaneous? Yes.
And it's spontaneous
Because it's negative. So delta G is the change in free energy. Change in energy going down is always favorable, right? Things roll down the hill. As they roll down, their potential energy decreases. Everything's going to lower energy, right? The entropy, positive change in entropy, is associated with spontaneity. And you think about, well, what happens if you drop a handful of marbles? Do they land in a nice geometric pattern on the floor? No, they don't. They go all over the place, right? And that's how I think of entropy. Any other questions?
Is that spontaneous at lower temperatures?
That's a good question. So this is saying for that reaction where we just calculated, there's some sort of a typo in that sentence. We ended up with delta G reaction. Oh, I see. Never mind. My brain is not working. We're supposed to calculate delta G at minus 55 degrees Celsius. So that needs to be in Kelvin. So the temperature is minus 55, and then we're going to add 273. Yeah, 218. And so it's asking us to calculate the value of delta G at that temperature. So delta G, then we're going to take our delta H minus 58.1 kilojoules minus the temperature times delta S. I'm going to put that into kilojoules again. Minus 58.1 minus 218 times negative 0.0733 negative 42.1 kilojoules. What did we come up with at the previous temperature?
Minus 36.
Negative 36.
More spontaneous.
Yeah, so more spontaneous at lower temperature. So at 25, it was 36.
Mm-hmm.
Yeah. At minus 55, it's 42. So it's becoming more spontaneous at lower temperatures. Any questions? On to the second method of calculating standard change in free energy. We can look up free energies of formation. And so we can calculate these in the same way that we calculate delta H, the change in enthalpy, from the heats of formation. So free energy of formation is a change in free energy when 1 mole of a compound in its standard state forms from its constituent elements in their standard states. Free energy of formation of pure elements in their standard states is 0. So this is very similar to the calculations for enthalpy. So delta G is the sum of the products times their coefficients minus the sum of the reactants times their coefficients. And the GF values just get looked up. So one of the reactions that occurs in a catalytic converter in your exhaust pipe is given here. It oxidizes carbon monoxide and nitrogen monoxide. Both of those are not good, and creates carbon dioxide and nitrogen, which are normal parts of air. So use standard free energies of formation to determine the standard change in free energy for this reaction at 25 degrees Celsius. Is it spontaneous? So what we're going to do is, here we have a table of standard molar free energies of formation. So we're going to say delta G for the reaction is, we're going to take the products. So we've got 2 moles of CO2, and over here CO2 in the gas state minus 394.4. And that's kilojoules per mole. The moles cancel. And then we've got nitrogen, and that's going to be 0, but maybe we forgot that it's 0. 1 mole times, we look it up, oh, yeah, 0. Okay? And we're subtracting the reactants. So 2 moles of CO minus 137.2 kilojoules per mole. Moles cancel. And we've got 2 moles of NO. We look up its GF, NO, plus 87.6. I'm coming up with minus 1238.4. Anybody else? Got negative 689. Well, maybe you're wrong, but maybe I'm wrong. So let's both do it again.
That seems kind of high.
I know, it does seem kind of high. That's kind of what bothered me. Yeah, I think I did it wrong the first time. If you want to get the answer correct, and let's be real, if you don't care about getting the answer correct, why are you even doing the problem, right? If you want to get the answer right, you should write some stuff down. Write this down with the units. Now, if you just mentally canceled out the moles, that'd probably be just fine. But you want to remember that this is in kilojoules, and it can get very confusing with all the negatives and subtracting negatives and stuff. If you've got this written out, then you get one answer, you clear the calculator, you run it through your calculator again. If you get the same answer, that's reassuring. If, like for me, I got 2 different answers, Trish already did it and confirmed that my second answer was probably the correct one. Otherwise, I'd run it through a 3rd time and go for best 2 out of 3, because it's unusual to make the same random error twice. Some people are extra lucky that way. Okay, so we calculated delta G. Is the reaction spontaneous? Yes, because delta G is less than 0. And I'm very big on answer all the questions. Okay, this is requesting 2 pieces of information. Calculate delta G and answer the question, is it spontaneous? So we can utilize Hess's law to calculate changes in free energy. Hess's law is where if you can imagine a chemical reaction as the sum of a number of steps, then you can calculate any state function associated with those, provided you know the values for the steps. It doesn't actually have to occur that way, because the state function doesn't depend on exactly how you got there. It's just where you started, where you ended up. So same relationships for enthalpy apply to free energy. So if you multiply the equation by a factor, then you multiply delta G by a factor. If you reverse it, the reaction, you change the sign on delta G, and then we can add these things together. So find delta G for this reaction. So what we want to do here is we want to figure out how we can combine these equations so that they add up to this one. This just ends up being sort of a logic puzzle. I tend to start with the first equation, and what I'm going to look at is are any of these things on the right side of the arrow? So here I have NO as a reactant, but in my ultimate answer, I want to have NO as a product. I have NO2 as a product here, and here I have NO2 as a reactant. So that tells me I need to reverse this reaction, write it backwards. So I'm going to write 2 NO2, and I want to line up all my arrows. So 2 NO plus O2. And then delta G for that is going to be the opposite in sign. So it's going to be plus 71.2. Now I'm going to look at the next equation. N2 and O2 don't show up in my final reaction at all. NO, though, is one of the products. So I'm going to leave this one alone and toss it in here. So I'm going to have 2 NO over there. I have N2. We did things like this in 1A. Maybe you hope that you'd never have to do that again, but oh, here it is. I didn't do anything to the equation. I don't do anything to delta G. Let's look at this last one. We've got N2O as a reactant, and then those guys. N2O is supposed to be a reactant, so this one also I will put in the same direction. So now I'm going to look at, when I add these together, do I get this result? And the answer is, well, not quite. So some of these things are going to cancel out. I'll change colors here. There's N2 and N2, O2 and O2. So those canceled out. There's an extra O2. This is looking impossible, isn't it? Pause. So it became apparent that this was just not possible. And, oops, looking at that then, because I could cancel out the N2s, but I couldn't get rid of the O2s. And there was just no way around that. And then looking at this equation, I've got 4 nitrogens here and only 2 there, because there's supposed to be a 2 in there. Just that wee little typo. So that puts a 2 in there. Okay, so this is going to go better. And we're back. Okay, so we need to make these things work out. I've got 1 mole of nitrogen over there and 2 moles over here. I've got 1 mole of oxygen and 2 moles of oxygen over here. So that tells me I need to take this middle equation and multiply by 2. So I'll put 2's there. This 2 becomes a 4. And then I'm going to multiply delta G by 2. I did that so that 2 N2s cancel and 2 O2s cancel those over there. Then I'm looking in to see if anything else cancels, and it does not, so I'm going to copy things down. You get 2 N2O plus 2 NO2, and that's going to make 6 NO. And that's my desired reaction doubled. That's okay, we can get there. So delta G for this one is the sum of those things, 71.2 plus 175.2 times 2 plus negative 207.4. So 214.2. And then I need to divide this by 2 to get my desired reaction. So I'm going to divide this by 2. And No, we don't want to watch you do that all over again. 107.1 kilojoules. So which method do you like better? The free energy change of formation is the fastest. But if you don't have that information, what are you going to do? You got to do something else. Is this reaction spontaneous? No. Not at this temperature. So we're calling this the Gibbs free energy. Why is it free? Well, we usually want to take the energy that's released by a chemical reaction and make it do some work, right? Make it do something. So we've got combustion of gasoline in the engine, and we want it to move the pistons and turn the axle and cause the car to go forward, right? So the change in free energy of a chemical reaction represents the maximum amount of energy that's available or free to do work. And many times that change in free energy is less than the change in enthalpy. The change in maybe also releasing energy to the surroundings, but not all of that energy is available to do work. So in this illustration here, we've got solid carbon in the graphite form reacting with hydrogen to form methane, and that's an exothermic reaction. It releases 74.6 kilojoules per mole of heat energy into the surroundings. But the minimum amount of heat that's lost to the surroundings is 24.1 kilojoules, and so the maximum amount of work that you can get out of this is 50.5 kilojoules. This heat loss to surroundings is like the heat tax. Every transaction, you lose some of the energy. So that change in free energy is a theoretical limit. You can't always attain that. In fact, I don't know that we ever can. In a real reaction, the amount of energy available to do work is going to be less than the change in free energy, the Gibbs free energy, because we also lose energy as heat. Only reversible reactions can reach the theoretical limits because reversible reactions can occur infinitesimally slowly. And so that reminds me of calculus class, where you talk about area under a curve and you look at these infinitely small things, right? So infinitely small incremental changes in this reaction, you can have the free energy match the amount of energy produced. So example of a reversible process. So here we have a cylinder, and there's a gas down here, and then there's this disc here, and we put sand on it. The sand is pushing down on the gas. If we take a grain of sand off, then the gas will expand a teeny tiny bit. And if we take another piece off, and so we're removing the sand one grain at a time. Very, very tedious. So incrementally removing sand, the weight of the sand is going to exactly match the pressure at each increment. It's a reversible process. We could also go the other way and add a piece of sand, and it would go back down. All real reactions are irreversible and do not achieve that theoretical limit. When you draw current from a battery to do work, some energy is lost as heat because there's resistance in the wire. And you know that, a lot of times you've been using your phone a lot and it gets warm, right? It's the energy lost from the battery. When you recharge the battery, it takes more energy to recharge the battery than the work that was done in discharging the battery. And so you're just always losing. It's kind of depressing. So battery discharging and charging, discharging and charging. You can get the system to return to its original state, but the surroundings don't. So you can make the battery go back to where it was, but that's going to result in a change in the surroundings. And the result of that is a permanent dispersal of energy into the surroundings. So if we have a reaction with a positive free energy, something that's non-spontaneous, that delta G represents the minimum amount of energy needed to cause that reaction to occur. In actuality, you're going to have to put in more energy.